Okay, so I'm actually going to rub this out, but I'm just kind of working straight underneath because I notice I can't see that very well on the screen. So I'm now going to just apply this for y equals log of ax base e. Okay? And so I'm just going to use my log law to break this up. So how can I write this in a different way?
ln ax.
Yeah, ln x plus ln a, or ln a plus ln x, same thing. Okay? So remember, when they've been multiplied together, you can break that up into addition. Okay. Now, what can you tell me about ln a? We're differentiating with respect to x.
It's 0.
It's not 0, but it differentiates to 0. It's a constant, okay? So I'm not sure what it is. A could be 2, and I have ln2. ln2 is just a number, okay? It could be 5. ln5 is just a number. So a constant differentiates, like Brian said, to 0, okay? So this then means that y dash is going to be differentiate ln x, which is what we just did. Can you remember what that differentiated to? 1 over x. And then that becomes 0. So actually, this also differentiates to 1 over x. Well, what it means, Amy, it's quite interesting. So it means that y equals ln x differentiates to 1 on x, but y equals ln 3x also differentiates to 1 on x. They have the same gradient. Gradient curve. But at the moment, I'm showing you where the rules come from. I'll show you a different way to apply it soon. We'll use it from the formula sheet. Okay? It is, but it's quite, oh, sorry, Luke. So it was not really needed in terms of the proof. I was just giving an example, okay? But I'll show you a method. Like, I wouldn't think of it like this as I differentiate these, okay? We're just kind of proving at the moment. Okay, so if we had a situation like this, so we're talking about y equals ln 3x plus 2 or something like that. Okay. What we'll do is we'll let u equal ax plus b.
Did we press record again?
Yes, I did. Thank you.
Okay.
Okay, so I'm just going to make it look a little more simple. Okay. So this would be y equals ln u or log of u base e. Does that seem okay? Now, on my formula sheet, I have this chain rule that we use to come up with our other chain rule that we use as a process. But also we've chain ruled in extension, for those in extension, when we did our rates of change. Remember when we had to break it up and have it cancel out? So this is from the formula sheet that if u is equal to f of x, dy on dx is equal to dy on du times du on dx. So I don't want you to be particularly worried about this, particularly if you're just doing advanced, because it's not something that you particularly need to use. We've used it in extension, but what you can see is we've got dy on the top, dx on the bottom. We've got a du on the top, du on the bottom. So it's just that we've manipulated. They cancel out to become dy on dx. Okay? So it's just a manipulation. So we're trying to find dy on dx, which means we need dy on du and du on dx. Yeah? To follow this formula. U is f of x, which in this case is ax plus b. Yeah? This is just formula, oh, FS, I apologize. No, I thought you said F of X. Yeah, FS is formula sheet. So this has just come from the formula sheet. Okay, so we want to find dy on dx. We're going to use this formula. So dy on du says differentiate ln u with respect to u. Okay, and what's that going to differentiate to? This is the thing that we just came up with. 1 on u. Okay, not 1 on x because it's with respect to u. Okay, 1 on u. That's this bit. And then du on dx. Okay, so we're differentiating u with respect to x. If you need to separate, we're going to separate. Okay. How do you differentiate ax plus b? You can think of it as a nice numerical example. How do you differentiate 3x plus 2? You end up with just a. Okay, so 3x differentiates to 3, 2 differentiates to nothing. So this, Joel said, differentiates just to a. Okay. So dy on dx is dy on du, which is 1 on u, times du on dx, which is a. And so we end up with a on u okay, but there's actually a problem with this. I made up u. Okay, like I said those words myself. So proud, Alicia. Okay, so I do need to just pop x back in. Okay, so that's a over ax plus b. Okay, now this is the proof. Don't write, well you can write these examples. I'm just going to do a couple of examples, and as we do the proper examples, I'll show you how it works, because this isn't quite how I would think of it, but just to show you. Okay, so if you have, let's do that one that I just wrote there. We've got y equals ln 3x plus 2. It differentiates to a, which is 3, right? Now, let's think of a in a different way. If I differentiate 3x plus 2, I get 3, right? So basically what I'm doing is differentiating what's inside the bracket there, and then I keep what's inside the bracket in the denominator. That's how you differentiate logs. Differentiate what's inside the bracket, goes on the top. Keep it exactly the same, it goes on the bottom. There's no log in your gradient. Okay, so that's how I'm applying this. So like I said, you don't need to reproduce this at all. I hope it was interesting. Also that implicit differentiation is pretty awesome, just saying. Okay, so I'm going to go on to some examples, and it will make more sense. So if you're feeling a bit like, oh, I don't know what's happening, that's okay. We're doing a proof. We're going to learn how to apply it. Can I rub that off? Yeah. Okay? Alrighty. So, here we go. When you differentiate a log, you ready? And let me clarify, sorry, a log base e. We will differentiate logs with base e. Okay? You differentiate what's inside the bracket. X differentiates to 1, and then you put that in the denominator. It's 1 over x, okay? And that's the thing we came up with first, but this is the process. So this is how I would think of how I differentiate logs. I'll bring your attention to the formula sheet in a minute, okay? So this one here, it's a log base e. It's exactly the same as the first one, okay? I differentiate what's in the bracket, and it's 1. I put what's in the bracket in the denominator, that's x. Okay? This one here, I differentiate what's in the bracket, and I get 4, and then over 4x, and then that cancels to 1 over x. Now that, if you remember the bit that we just came to where I went for ln x and then changed it to go for ln ax, and we came up with the same that it differentiates to 1 on x, this is y, because those cancel out. Okay. Alrighty, this next one, differentiate what's inside the bracket. That becomes 2 and 2x plus 1 in the denominator. Can I cancel the 2's? Okay, because of this plus, right? Alrighty, so let me bring your attention to the formula sheet. I think that you should know the process of differentiating logs, but I also think you should be able to interpret the formula sheet. Also, because there are some extra things on there that just might be helpful to you, particularly thinking extension. Sometimes they like ask questions for something that's just on there that you can just apply it. Okay, so if you have a look, it says on the formula sheet, if y equals ln f of x, then dy on dx is equal to f dash of x over f of x. Okay, so ln something, okay, differentiates to differentiate that something over the something, yeah? Which is exactly what we've been doing, okay? So, now we have a look here. If you're differentiating x squared plus 5x, you differentiate x squared, and then you differentiate 5x. You happy with that? Same here. You differentiate ln 2x, and you differentiate 5x. The 2x, it's not joined together or anything. There would be a bracket there. Okay? So that's going to differentiate the 2x, and then 2x on the bottom, and then 5x, look, turn around. You don't need that ruler. There's no reason for you to have a ruler at the moment. Differentiate 5x, and you get 5. No further comment needed. Okay? Here, 2 over 2x is equal to 1 over x plus 5. Do you need to make a denominator of x and then put them together? Like I would leave it here. Okay?
When you're differentiating, say, log base e2x, you did 2 over 2x, can you just go straight to
You can just write it as 1 over x, yeah. I'm not going to just because I'm doing it as a process, but it's totally, yes, I think that's a good thing to do. Okay, what do we identify that we have here? X squared, yes, but it's a product. Can we see that? You've got u and v. Okay, so go and write your list and then use the formula. Okay, so we're learning about how to differentiate new things, and then we're just putting it all together with what we've done before. Okay, product rule, quotient rule, chain rule. We can apply them all to everything that we're looking at. Okay, so I'm hoping that you're done or on the way. Okay, so differentiate what's inside the brackets goes on top, and then what's inside the brackets is in the denominator. I'm looking at my product rule from my formula sheet, u times dv on dx plus v times du on dx. I'm going to put the 2x out the front. What's x doing some cancelling there. Okay, is this equal to 3x ln 2x? No, okay, because they're not like terms, because this term's got ln 2x in it, right, which is algebraic, not like term. Okay, that's it. You could take out x, I don't know why. Rachel?
Is it better to write ln than
I just mostly write it because it's shorter. It makes no difference. I don't care what you write. Log base e, ln, that's really the reason I write it because it's shorter. Okay? Alrighties. Keep going if you haven't already. Oh, I'm sorry, did I? Yes, you could have taken out the x, Amy, but I don't really think there's any need to. Okay. Yeah. But not the, like the 2x is locked into the ln, Jamila. The 2x is locked into the ln, it's just the coefficient. Okay. Differentiating logs is really, really easy. Okay, it's really easy once you know what to do. Now, you can imagine that integrating is somewhere, so that's when we go backwards, is somewhere that people don't identify that it's a log because there's no log to be seen, is there? But that's something we'll look at as we integrate. Okay, what do we have in 3b here? A quotient. Wonderful. Okay, so just keep applying your rules. In case you didn't hear that, that's festy. Okay, so I haven't simplified this denominator, which normally, actually, honestly, I would. What is e to the power of x squared? E to the 2x, okay, but I am kind of looking and going, well, I've actually got e to the x in each term here. So I'm thinking of it as I'm taking out e to the x and I'm going to cancel that out, yeah? And, you know, do I want to get rid of the fraction that's in the fraction?
No.
Kind of, but no. Like, honestly.
How do you know that? Yeah, how did you know that?
Because
Yes, thank you.
he is a mind reader and a genius.
I'm right.
Why are you so surprised? You feel offended?
Sure.
Okay. So I'm going to leave it like that. I mean, we could change it around, but okay. Next one. Not difficult. Okay, don't let this put you off. Follow your process. Differentiate what's inside the bracket. What does that become? 3x
Squared.
Oh.
Keep the denominator as the expression in the brackets there. Can you cancel out x squared and x cubed?
9.
Definitely not, because of that plus 1. That's it. Done. So easy, right? Same here. Very easy. What does this differentiate to? 2x plus 2? It's totally fine to have multiple terms in your numerator. Okay? And then this remains the same. Oh, I'm not sure, but I'm having a look if I can do some cancelling here. I just have a quick check. So,
No, I don't think you can.
oh no, if it was an x plus 2, that one, doesn't it go to minus 2 plus, oh no, because it's product of minus 1. Ignore, leave it.
Unless you
You
took
can
negative
take
2 out
the
of
2
both.
out, but... Okay, so this one here is just what I showed you from the formula sheet. I'm not quite sure I've left a whole slide for it. That's it. That is it. Wow. Okay, just what we talked about before. Differentiate for the top, leave it the same for the denominator. I might just have a look at this one. I think too many examples. I think we're okay. Right. Although this one's kind of interesting because you could pull the 4 out, or you could keep it in. You'll still get the same thing. Like, because remember the log law? Like, this is the same as 4 ln x, right? So it's 4 of x. Or you could differentiate and it will cancel to still come up with 4 over x. Okay, so this one here, because we've done a number of them like that. So, we need to be careful here. Can you see why we need to be careful here? How do I differentiate x squared plus 1 over x? I use the quotient rule. So I'm kind of doing a differentiation in a differentiation. It feels a little bit complicated, okay? So I'm going to have my u and my v. Like, having said that, it does, you know, would it be better to... No. I was just thinking, because we could do x squared over x is x plus, maybe it is. Yeah, actually, I take it back. This would be nice to do though.
Yeah,
Do it as a point. Okay. I'll do it, and then I'll show you how we could have made it easier for ourselves. Okay. No, because the idea of it is a good thing to look at. Okay, because we want to be able to apply what we know to harder situations and not be too fazed by that. Okay, so f dash of x is going to be u dv on dx, which is x squared plus 1 times 1. Oh, sorry. Quotient rule. V du on dx, so x times 2x minus u dv on dx, so that's x squared plus 1 times 1. What's wrong with this picture? Very wrong. Oh, okay, so I'm going to subtract that whole thing there. Now, note that this here is f dash of x. You with me? Now I need to divide by f of x. So the way that I'll do that is divide by f of x. and this is f of x. Yeah? And so I'm going to flip and multiply. I'll tidy this up a bit. So that's 2x squared minus x squared minus 1 times, okay, so I'm flipping and multiplying, x on x squared plus 1. And, sorry, this is going to be so much more simple the other way, but anyway, that's cool. This is good, a good application, though, and not the best way to go at all. Okay, so when something cancels out, it becomes 1, okay, not 0. So this times 1, that's going to just be x squared minus 1 over x squared plus 1. Okay, yes, this could factorize to x minus 1, x plus 1, but this, we're not factorizing. Okay, it's not x plus 1, x plus 1 or anything like that. So that's it. Okay? I simplified that bit. Okay, now let's go and do this. So I'll do the same question. Okay, but I'm just going to think about it differently. We're okay with this? I'm breaking up my fraction. Okay, and so x squared on x is x, and this is x to the negative 1. So, I mean, this is much nicer. So, I've got differentiate what's inside here. So that's 1 minus x to the power of negative 2 over x plus, I mean, I guess I still have to do a bit of work on it. I'm not going to, I mean, this looks pretty bad. Let's maybe leave it like that, Jamila. Oh, sorry, did I? Yeah, I got x squared. That is my f dash x. So that's v squared. I cancelled it here because I had that x to cancel it. Is that okay? Yeah? No? Okay. No worries. So this, I guess, I mean, it was much quicker to differentiate, but then if I want to make it look better, maybe I do a similar. Does this seem okay? So I've written that with a positive integer, positive power, x, and then divide, and then I'll make a common denominator. So it's x squared minus 1 on x squared. Make a common denominator, x squared plus 1 on x squared. Oh, have I made a mistake somewhere? Because I've got an x here that I don't have here. Yeah?
I think it should be x squared plus 1.
Oh, this one's not. Apologies. So this one's just a denominator of x. Sorry. Whew. Okay, so now I'm going to flip and multiply. I'm so comfortable with fractions on fractions because I have my method. I hate them, so I write them like this as division. Flip and multiply, super easy. Every time I see it, doesn't stress me out. That's my method. Okay, that's what you want to have your, I see this, I know how to deal with that, it's okay. Okay, we're not freaking out about things as we go. So we're coming up with the same thing, and then we get our little cancel, same. I don't know, I mean, like, you had to tidy it up quite a bit, didn't you? So it wasn't so bad going the other way. What do you mean? So actually. It's come out. I think the nicest. Yeah. So here's use the log law. That's pretty nice, right? Okay, so he's got division. He's made it a subtraction, and then now we get this. I like this. Thanks, Horace. Okay, and I probably would make a common denominator here, but it's not very hard. And we'll get 2x squared minus x squared minus 1. Which simplifies exactly the same. Isn't this one of the exciting things about maths, like that we have a lot of different ways to think about things, and logs are quite interesting because there's so much manipulation that it does give you options. Okay, so I'm actually not going to do any of the other examples. So we're going to start having a look at exercise 13.3. The other exercise from the trig you had been set already